Hi guys, we are starting a new playlist related to sorting algorithms. There are so many algorithms related to sorting, but we will discuss a major sorting algorithms that most people use, like bubble sort, merge sort, quick sort, insertion sort. In this video, we will talk about bubble sorting algorithm. Bubble sorting algorithm. So there are two ways of sorting, right? Like either we can sort in an ascending order or in descending order. In all these videos, we will sort the arrays or list in an ascending order. Okay. Now coming to bubble sort algorithm, let's assume we take this as an input array. If you see this array, this is not in sorted order, right? What should be the output after sorting? Let's write output here. What should it be? So after sorting, the output should look like this: 13, 21, 45, 101 and 102. Okay, the output should look like this post sorting. So how bubble sorting algorithm works? So bubble sorting algorithm, what it takes is it compares adjacent elements, and whenever it finds that both elements are not in sorted order, then it swaps it. Like let's take this is the input, right? So first what it does is it compares 13 and 7. I'll draw this here and show. Now this is the input array, right? What it does is it compares 13 and 7. Okay. Since we are doing sorting in an ascending order, the largest element should be at the end and the lowest element should be at the right left side, right? So if you see 13 and 7, 7 should be on the left side and 13 should be on the right side. So that's why whenever it compares the elements and if it finds that both elements are not in expected order, it swaps it. Here, both are not in sorted order. That's why if you see after this comparison, you see both got swapped. Like I swapped both elements, okay? And after swapping, my array looks like this: 7, 13, and the remaining elements are as is. Now next what you should do is, now let's compare these two elements. First two elements comparison is done. Now let's compare these two. Okay, these two are also not in sorted order. So what we have to do is we swap the elements. Okay, now I swap these elements, and 6 moved here and 13 moved here. Remaining elements are as is. So we compared first three elements, right? Now let's compare 13 and 45. Both are already in sorted order, so no need to swap. Now compare 45 and 21. Both are not in sorted order. Swap the elements. After swapping, you see 21 and 45 got swapped here. Now compare 45 and 9. Both are not in sorted order, so swap the elements. Now after swapping, if you see 9 and 45 got exchanged. Now compare 45 and 101. Both are already in sorting order. Now let's compare 101 and 102. Both are already in sorted order, right? So when we do like this, like this is the array, right? You just looped through the array only once. First pass, you call this as passes. So by the end of first pass, what it should be is the largest element among all these will get pushed to the end. So if you see here, my largest element is 102. It got pushed to the end. So by the end of first iteration, highest element get pushed to the end of the array. So in the second pass, second largest element gets pushed to the second position. In the third pass, third largest element gets pushed to the third position. In the fourth pass, fourth largest element gets pushed to the fourth position. Likewise, for at the end of each iteration, one element gets pushed to the end. So if you say bubble sort, like if you see the name right here, at the end of each pass, the largest element is going to the end. So it's getting bubbled up and it's getting pushed, right? That's why we call this as a sorted algorithm, bubble sorting algorithm. Now let's see the second pass here. So you see 102 is already sorted, is already at its correct position. So you shouldn't touch this 102, okay? So what we will do is we shouldn't touch this. We will only compare, and if required we swap only the remaining elements. That's why I'm marking this 102, so that we shouldn't swap, we shouldn't compare this because it is already at its correct position. Now if you see the second pass, what we have to do is, let's compare 6 and 7 now. Okay, let's compare 7 and 6. Both are not in sorted order. Then swap both. So when we swap both, 6, we have moved 6 and 7 at its correct position. Now let's swap these two. Both are already in correct position. Okay. Now let's swap 13 and 21. Both are already at its correct position. Now let's compare 21 and 9. Both are not in sorted order. So let's swap the elements. After swapping, you can see 9 and 21 are placed here. Now let's compare 21 and 45. Both are already in swapping, or already in correct order. So no need to swap. Now let's compare 45 and 101. Both are already in at its correct position. So no need to swap. So by the end of second pass, what we can see is 101, which is the second largest element, is at its correct position, is pushed to the end of the array. So in the third, like in the third pass, you should exclude these two. You shouldn't compare these two because these are already sorted. You shouldn't compare this. So I'm just marking it. Now let's see. Now let's compare the other elements. So 6 and 7. If you see 6 and 7, both are already sorted. No need to swap. Now let's compare 7 and 13. Both are already sorted. No need to swap. 13 and 9. These two are not in correct order. So we have swapped both 9 and 13. Now if you see 13 and 9 got swapped here, right? Now let's compare 13 and 21. Both are already in sorted order. No need to swap the elements. Now let's see 21 and 45. Both are already at its correct position. No need to swap. So by the end of third pass, even the third largest element gets pushed to the end of the array. Now let's see the fourth pass. In the fourth pass, since these three elements are already sorted, you shouldn't compare the last three elements, right? So I'm just marking this so that you shouldn't compare these elements. Now let's see the fourth pass, okay? So in the fourth pass, let's compare 6, 7. Both are already in sorted order. No need to compare. No need to swap. 7, 9. Both are already in sorted order. No need to swap. Now compare 9 and 13. Both are already in sorted order. No need to swap. 13 and 21. Both are already in sorted order. No need to swap here. By the end of fourth pass, even the fourth largest element is at the fourth position. Like fourth largest element gets pushed to its position, right? Now let's see the fifth pass. In fifth pass, you should exclude the last four elements because those are already sorted and its correct position. Now if you see here, now compare 6, 7. Both are already sorted. No need to swap. 7, 9. Both are already sorted. No need to swap. 9 and 13. Both are already sorted. No need to swap. So by the end of fifth pass, even the fifth element gets pushed to the fifth, like end of the array. Basically, end of the array is fifth position. So if you see here, now the fifth element is moved to its correct position. So five elements, by the end of fifth pass, last five elements are sorted. Now let's mark these five elements so that we will not compare in the sixth pass. Okay. Yeah. Now what we will do is we will compare here. Now let's see, compare 6 and 7. Both are already sorted, no need to swap. 7 and both are already sorted, no need to swap, right? So now by the end of sixth pass, even the sixth element, sixth largest element is at its correct position. So I'll mark this sixth one, 9, basically 9. By the like in seventh pass, you should mark all these six are already sorted. Okay. Now in the seventh pass, what we should do is, now let's compare 6 and 7. Okay. Both are already in sorted. No need to swap. Right. So what we'll do is we will mark this one 7 as sorted, but there is only one element left. If only one element is left and the remaining all are in sorted, then no need to do any comparison, right? So here what you have done is you have done 7 passes, right? So 7 passes means here length of the array, if you see here length of the array is 8. You have done 7 iterations or passes here. 7, which means length minus 1. So let's see the time complexity of this. Now in the first pass, how many comparisons you have done? You have done 7 comparisons. 1, 2, 3, 4, 5, 6, 7. Right? In the second pass, you have done 6 comparisons. 1, 2, 3, 4, 5, 6 comparisons. Right? So likewise, at the end, so number of comparisons you have done is in the first pass 9 n minus 1. In the second pass, you have done n minus 2. In the third pass, you have done n minus 3 comparisons. So likewise at the end, what you will end up doing single comparison at the end. So you have I have written down all the comparisons n minus 1 plus n minus 2 plus n minus 3 plus 1. Now here this is equivalent to n into n minus 1 by 2, which is nothing but order of n square. So the time complexity of this bubble sorting algorithm is n into n minus 1 by 2. Okay. This is the time sorting of the algorithm. But we have missed something here. If you see here, after the fourth pass, like if you see here in the fourth pass, you just compared it. Ideally you did not swap anything here. If you see the input of the fourth pass is 6, 7, 9, 13, 21. Even if you see the output 6, 7, 9, 31. Okay. Why did we even go ahead and did fifth, sixth, and seventh passes here? Because since at the end of third pass itself, in third pass we have done some swapping, like you have swapped 9 and 13, but in fourth pass you have not swapped anything. You just compared it, and but you did not swap anything. Even in the fifth pass you did not swap anything. Likewise, it went for sixth and seventh passes also. We can actually avoid this, right? So in fourth pass, when we came to know that we did not swap anything, we just compared, but we did not swap anything, we can ignore fifth, sixth, and seventh passes. So what we can do here is when we are doing an iteration, we can take a variable, something like swap. Okay, we can take some variable, some swap, and you can keep note of it, like if you have done really swapping or not. Let's say initially we can assume this variable as false, and if you have not done any swapping, the swap variable would be still false. In that case, we can ignore the further passes. So this will reduce the time complexity, right? Now this is like if you consider this swapping variable, let's say the array is already sorted. Let's assume that our input is 6, 7, 9, 13, 20, 13, 21, 45, like this. This is already sorted, right? In the first pass itself, we will get to know that we did not swap anything. So our algorithm ends here. At the end of first pass, we will know that the algorithm, that array is already sorted, and we need not go to further passes. We can stop here. So the time complexity, if the input is already sorted, is order of n, because we just did one iteration. One iteration means one, like we have just passed through the loop only once, which is nothing but order of n. So if the array is already sorted, which is the best case for us, the time complexity would be order of n. So best time complexity would be order of n. And worst time complexity comes when the array is sorted in reverse order. Let's assume we have to sort array in an ascending order, but the input is in descending order. So you have to go through all passes and then swap it. That would be our worst time complexity. In worst case, the time complexity would be order of n square. And our average time complexity is also order of n square. You don't need any extra space here, because if you consider the space complexity of this, you're doing in memory, right? You're not consuming any extra space. So time space complexity would be order of 1. Now let's implement this algorithm using Java and let's write some code. I'm using IntelliJ as an editor. Consider this input. First, we have to declare number of passes, right? Number of passes are nothing but length. Like let's say you take array dot length, then I plus plus. Outer array is for number of passes and internal array is for comparisons inside each pass. So for int j equal to 0, j less than array dot length minus I minus 1, j plus plus. Why did you use this? Because in the first pass you have 7 comparisons. In the second pass you have just 6 comparisons. In the third pass you have just 5 comparisons. Your number of comparison decreases with increasing I. That's why you have added this I minus 1. So now if the left element array of j is greater than right side element array of j plus 1, then you should swap, else you should not swap it. That's why if it is greater than, then I'll take array left side element into a temporary variable and then I swap it. Temp. So now we are done with sorting. But remember, we to improve this algorithm, we spoke about swap variable. So where should we put that swap variable? We have discussed, right, in a pass. If you see that there is no swapping, then we can come out of the passes. That's why we will declare swap variable here. Initially, the swap is false. When we see that swap had occurred, then we change the value to true. Now here what we can do is, if swap did not occur, which means if the swap is false, then break, come out of the loop. Okay, now let's print the output. Let's print the output of this one. So if you see the output 6, 7, 9, 13, 21, 45, 101, 102. This is sorted. Now let's take input in, let's take an descending array. Like the array is sorted in descending order, which is our worst time case complexity. 7, 6, 5, 4, 3, 2, 1. If you see, the array got sorted properly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's take the array which is already sorted. So that is sorted. So this is our best case, and the array which is in descending order is our worst case, and the initial input is the average case. Yeah. So we ran for all the three scenarios. That's it for this video. In the next coming videos, we'll talk about the other sorting algorithms. Thank you.